Greetings, my name is Wan Alaris bin Wan Sarman with the matrix number CD240212.
Hi, my name is Bimal Alaki Murugisan. My matrix number is CD240061.
Hi, my name is Steven Nair. My matric number is CD240251.
Assalamualaikum. My name is Shafiris Haikal bin Syaharin. My matric number is 240110.
Good evening, my name is Zachariah Austin and my matric is CD240166.
This experiment focuses on the behavior of thin cylinders under internal pressure. Thin cylinders are commonly used in various industries such as food processing and oil and gas to contain pressurized fluids. The primary objective of this experiment is to understand the stress distribution in thin cylinders with open and closed ends. By measuring the strain in different conditions, students can observe the differences between uniaxial and biaxial stress states. The experiment involves using mechanical and software-based pressure gauges to record the strain values at various pressure levels, providing insights into the mechanical properties and stress responses of thin-walled cylindrical structures.
Okay, so I will be presenting about the additional theory for our thin cylinder lab. So what is a thin cylinder? A thin cylinder is a structure designed specifically to hold pressurized fluids. It's built to withstand the internal pressure exerted by the fluids inside. These cylinders are extensively used in the industries like food processing and oil and gas, typically in the form of tanks and pressure vessels. The robust yet precise design makes them indispensable for safely storing and transporting fluids under pressure. If you look at figure 1, you'll see the cross-section of the thin cylinder. The internal pressure is represented by Pi, while Di and T refers to the internal diameter and wall thickness, respectively. These parameters are crucial in designing a cylinder that can safely contain pressurized fluids without failure. Okay, moving on. A vessel with a 10:1 ratio of inner radius to wall thickness is called a thin cylinder. The wall's tension in this instance may be regarded as uniform. Inside the cylinder, the material will be subjected to three principal stresses that are perpendicular to each other, which are longitudinal, radial, and hoop stresses. Sometimes spheres with thin walls are also used. As seen in the image below, consider a sphere with an internal radius of r that is under internal pressure of P. Because of symmetry, the longitudinal and circumferential stresses that are formed on a sphere's surface are of equal magnitude, and both stresses are main stresses when there is no shear stress. Okay, so for the results of our first experiment, which is the experiment for thin cylinder with open ends and a pressure of 5 until 30, the second until the fifth gauge shows an increase in all the values. However, for the first gauge, it shows a decrease of value up to a negative value. For our second experiment, which is the thin cylinder with closed ends experiment, at the pressure of 30, all of the gauges shows a different value respectively.
Today I'm going to present about observation thin cylinder experiment. The first point is pressure measurement. For mechanical pressure gauge, it increases immediately as the hand wheel extends. Next, we use SM1007 software, which is pressure reading stabilizer after 2-3 seconds. The next point is initial setup. A virtual strain meter display non-zero value before processing the zero all gauge button. Next, we go to the strain gauge reading. The first point is thin cylinder with open end, which is strain gauge 13456 will show the positive value as pressure increase. Next, strain gauge 2, it will show negative value for 0.5 to 3.0 megapascal. Next, thin cylinder with closed end, which is at 3.0 megapascal or strain which 1 to 6 show positive value. We go to the next point, which is strain comparison. First, strain gauge 1 and 6. Similar reading for open and closed end cylinder at 0.5 to 3.0 megapascal. The last one is stress data. The first one is open end, which is it only hoop stress recorded. The last point is closed end. Both longitudinal stress and hoop stress recorded. That's all for me. Thank you.
Now I will explain about thin cylinder calculation. The thin cylinder lab experiment is designed to help students understand how to thin wet cylinder behave under internal pressure. Here a simple breakdown of the key concept, produced and calculation involved in this experiment. Firstly is calculate stress and strain, hoop stress, O per H, and then longitude stress. Second calculation is determine the Young modulus from the relationship between stress and strain. Then plotting stress versus strain help visualize the relationship. The last one is calculate Poisson ratio using strain measure from different gauges. This show how much lateral strain occurs when there is axial strain. In summary, analyze this Whorler stress is involve calculating both hoop and longitude stress using a stabilized formula that relate internal pressures to material dimension. Understanding this principle is crucial for application in mechanical engineering, particularly in design, pressure vessel and pipeline. That's all from me. Thank you.
Student can access strains in a cylinder under two different end conditions, open and closed. In the open end condition, the cylinder experiences no axial load, leading to an absence of direct axial stress. Conversely, in the closed end condition, the cylinder is subjected to axial loads, which result in direct axial stress. A hand wheel on the frame allows students to set this condition. When conducting experiments, students select between the closed or open end condition based on their testing requirements. A thin-walled cylinder with open ends was subjected to uniaxial stress. In this open end condition, only hoop stress is discharged because the pistons are pushed out from the cylinder's end cap when the hand wheel is turned, resulting in no axial force on the end caps. Conversely, in the closed end condition, the thin-walled cylinder experiences biaxial stress, which includes both hoop stress and longitudinal stress. This occurs due to the contact between the pistons and the cylinder end caps, allowing the axial force from the pressurized oil inside the cylinder to be transmitted to the end caps. Consequently, axial tension is necessary to balance the fluid pressure exerted by the pressurized oil.
For a conclusion, the thin cylinder experiment provided valuable insights into the stress distribution and deformation characteristics of cylinders under internal pressure. It demonstrated that a thin cylinder with open end experiences uniaxial hoop stress, while a cylinder with closed ends undergoes biaxial hoop stress and longitudinal stress. Strain values increased with pressure in both conditions, and the results highlighted the differences in mechanical behavior between the two configurations. However, challenges with measurement precision, equipment stability, and calibration affected data consistency, such as showing a delay in pressure readings compared to mechanical gauges. These issues required pressure to be gradually increased and maintained for accurate strain measurements. To improve future experimental reliability, more frequent calibration routines and the use of advanced sensors are recommended. These measures will enhance accuracy, ensuring more consistent and reliable results, ultimately providing a deeper understanding of thin cylinder behavior under varied conditions.